Hi everyone and welcome back. In the last video we explored all the tools and settings inside Blender's motion tracking workspace. And I also showed you how to do plane tracking. Now it's time to put that knowledge into practice and track an entire shot from start to finish. Let's get started. Welcome to the second episode of motion tracking in Blender. This time we're going to do some camera tracking. First, I'll show you the quick method to track your footage and solve the camera motion. Then I'll go over the manual method, introducing a few new tools and explaining things in more detail. Finally, we'll start setting up our 3D scene. Let's jump right in! First, let's recap what we did last time. We turned our footage into an image sequence and imported it into the motion tracking workspace. Then we matched the resolution and frame rate to the footage. Next, we set the view transform under color management to standard. And finally, we set the scene frames and prefetched our footage. Now, let me show you the quickest and easiest way to camera track your footage. Click Set Scene Frames and prefetch if you haven't already done so. Next, hold Ctrl and left click to add a marker and check its size. Remember that you can display the search size by enabling it in the Clip Display menu. In Blender 5.0, this can be found under Viewport Overlays. You just want to make sure that the marker is not extremely small or extremely big. The pattern size should be big enough to cover most small detailed features in your footage. The search size should be large enough for the tracked feature to stay within the boundary in the next frame. You can test this without tracking by placing a marker and pressing the right arrow key to move forward one frame. In this footage, the motion is quite slow, so the tracked feature will clearly stay within the search area for each frame it's tracked. The default pattern and search sizes are fine here, so I'll just press X and delete the marker. Next, choose Affine as the motion model. Affine is the most versatile motion model. It might be overkill for some footage. For example, if your footage has very little perspective change or camera movement, a simpler model like location, rotation and scale would work just as well. But since this is the fast method, and if I had to pick one motion model that works for almost everything, I'd go with Affine. Just keep in mind that a more advanced motion model takes more computing power, but if your system is fast enough, it usually gives the most accurate results. For the match type, I'll choose Previous Frame. It looks for the pattern in each previous frame instead of the original keyframe. This is suitable for quick tracking with minimal manual adjustment. Then enable Pre-Pass to run an extra calculation for better tracking. Also enable Normalize to allow for better tracking in changing lighting conditions. Under Tracking Settings Extra, increase the correlation value to 0.9. Correlation controls how closely each frame must match its reference pattern. With the match type set to previous frame, that reference is the last frame. With keyframe, it's the original keyframe. If the match drops below this value, Blender stops tracking that marker. Setting it to 0.9 makes Blender stricter and helps prevent drifting. Then press Detect Features to let Blender find the best places to put markers. Right now, there aren't enough markers. We need a larger sample of tracks for Blender to calculate the camera motion accurately. To get more markers, open the Detect Features pop-up menu. The only settings we'll focus on here are Threshold and Distance. Threshold controls how selective Blender is about what it considers a trackable feature. Set it to 0.01. Lowering this value makes Blender less picky so it finds more points, even weaker ones, giving us more markers to work with. Distance controls how far apart those markers are placed. A higher number spreads them out more evenly, but we'll lower it to 80. This allows Blender to place markers a bit closer together and find more suitable tracking points. Now that we have more markers to work with, let's track them forward. With all the markers selected, press Ctrl T to track forward until the end. This gives us tracking data throughout the footage, which you can see in the graph editor at the bottom. However, only some markers are tracked all the way to the end. Most of them go off frame before that. To get more even tracking data across the footage, we'll also track backwards from the end to the start. Click Detect Features again, then press Shift-Ctrl-T to track the selected markers backwards until the start. Now we have more evenly distributed tracking data in the graph editor, both at the beginning and the end. Tracking once forward and once backward like this is often enough, but to get even more accurate results, you can also track forwards and backwards from multiple points along the footage. Drag to open a new window and set it to timeline so we can scrub through the footage more easily. I'll track forwards and backwards at 2 evenly spaced points along the clip. Go to frame 80, click Detect Features, and press Ctrl-T to track forward to the end. Then go back to frame 80. The detected markers are still selected, so we don't need to click Detect Features again. Just press Shift-Ctrl-T to track the selected markers backwards from the same frame. Next, go to frame 160 and do the same thing there. Click Detect Features, press Ctrl-T to track forward, go back to the same frame, and then press Shift-Ctrl-T to track backwards. Now we have plenty of tracking data evenly distributed throughout the entire clip. The next step is to solve the camera motion. To do that, go to the Solve tab in the left tool panel. Enable keyframe, focal length, optical center, and radial distortion. I mentioned where you can input these manually in the camera information part of the last tutorial. But for quick tracking, or if you don't know these values, it's totally fine to just let Blender calculate them for you. Then click Solve Camera Motion. The first time you do this, it might take a while, maybe up to 10 minutes depending on your computer. That's because we enabled keyframe, and Blender spends a long time finding 2 frames where the camera movement is the most different and where many of the same markers are still visible. It uses those as a starting point to estimate the camera motion, and then refines the solve across the rest of the footage. Once the solve is finished, you'll get a solve error. An error below 0.5 is good, but I'll aim for an error below 0.3, which is excellent. To reduce the solve error, go to the Cleanup drop-down menu. Then click Clean Tracks. In the pop-up menu, increase the reprojection error value to select the worst tracks. The higher that number, the less accurate the track. It's best to increase it to a point where only a couple of the worst tracks are selected. Then press X to delete them. Now let's solve the camera motion again. But wait, before doing that, disable keyframe. Blender has already chosen 2 keyframes for estimating the camera motion, so it will be a huge waste of time to wait for that again. Take note of the current solve error. Then click Solve Camera Motion. Without keyframe enabled, the solving process is much faster. As you can see, now we also have a much lower solve error. Now I'll just repeat the cleanup process until I get a solve error under 0.3. Press Clean Tracks, increase the reprojection error until only a couple of the worst tracks are selected. Delete those tracks, and then solve again. After doing this a couple of times, I finally have a solve error of 0.28. You can continue cleaning tracks to get it even lower, just be careful not to delete too many. Blender won't have enough data to solve accurately. You want plenty of tracks covering both areas close to the camera and far away. A final thing I want to mention is that you might have gotten a warning message at the bottom saying that some data failed to reconstruct. If you're unsure whether you got this message, it's totally fine to just solve the camera motion again to see if it appears. If I click on it, the last entry in the log just says "See console for details." So let's do that. Go to Window and click Toggle System Console. This opens a new window with more detailed information about the warning. It mentions that Blender was unable to reconstruct positions for tracks 241 and 243. That's great, because now we can find those tracks and delete them. The quickest way to find those tracks is to first change the movie clip editor from graph to dope sheet. Here we can see all of our tracks, but they're listed by their average solve error. In the drop-down menu to the right, change the sort field from average error to name. Now the tracks are listed according to the numbers in their names. Hold Shift over the dope sheet timeline and use the mouse wheel to scroll down until you find the problematic tracks, 241 and 243 in this case. You can see that these tracks only have a single keyframe at the end of the clip. That's not enough to calculate any useful tracking data, so select them and press X to delete. Finally, solve the camera motion again. You'll see that the warning message no longer appears. Let's change the movie clip editor from dope sheet back to graph again. Now we have a full, clean track with a good solve error, and that's how you can camera track quickly in Blender. At this point, you can skip ahead to the scene setup section of the video. However, I highly recommend watching the manual motion tracking process. 9 times out of 10, I'll use this quick method to camera track footage. And if you followed along, I recommend saving your file and using the tracking data we've already solved. However, you might come across situations where Blender can't detect features accurately, or cases like object tracking, where you'll need to track and adjust individual markers. Furthermore, there are still many tools and settings I'd like to show you. So now that you already have a solid track by following the quick method, you can just sit back, relax, and learn some additional things that might come in handy in the future. The manual tracking process starts out no different from the quick one. First, set scene frames and prefetch the footage if you haven't already done so. I'll leave the pattern size and search size at their default values for now. Next, for the motion model, this time I'm going to think about what I actually need. The camera is moving forward, rotating, and scaling parts of the scene, and in this tutorial, we're just adding a model in the middle of the tunnel. For this shot, location, rotation, and scale work perfectly because we're placing the model right in the center where the motion is mostly straight and even. But if I wanted to attach something to the side wall or ceiling, the features there would also appear to move sideways or upward as the camera moves closer. That slight diagonal motion is what Affine can handle better. If I used location, rotation, and scale for something like a poster on the side wall, it will probably still look fine, but the perspective might feel a bit too flat or rigid as the camera moves. With Affine, Blender can capture that slight skew and perspective change more accurately, so the poster matches the wall's angle more naturally throughout the shot. That's why I went with Affine in the quick tracking method. It gives you more flexibility when matching 3D elements to angled surfaces, though it can be a bit slower and sometimes makes weaker tracks drift more easily. I'll overlap the two shots and switch between them so it's easier to spot the difference. Now you can see that Affine gives a slightly more natural perspective, following the distortion and angle of the surrounding area in the shot more accurately. However, the difference is minimal. In the end, you'll need to choose a motion model based on where you plan to place your elements and how the scene will be used. Anyways, since we'll place the model in the center where there's barely any perspective change or skew, I'll stick with location, rotation, and scale, just to show you that it works perfectly fine in this case. Next, I'll set the match type to keyframe. In the quick method we used previous frame, which works great for automatic tracking because we're dealing with hundreds of markers. But in manual tracking, we only have a couple of hand-placed markers, and each one really matters. That's why I'm using keyframe this time. It keeps each track locked to its original pattern, so I have more control and consistency while adjusting them by hand. Leave pre-pass enabled again. Since the lighting doesn't change that much in this shot, you can leave normalize disabled. I often leave it enabled just as an extra precaution, but let's try without it this time. For quick tracking, it's a helpful extra layer that can improve consistency. Place a marker at a point of contrast in the clip with Ctrl left click. Make sure the pattern size covers the entire pattern you're trying to track. Make sure the search size is large enough to follow the pattern between frames. Remember that you can move, rotate and scale markers with G, R and S. You can shift left click to select and deselect the inner and outer boundary separately to transform them individually. In the left track panel in the track drop-down, there are a few different options for tracking. By hovering over the buttons, you can see what they do and their shortcuts. You can also find these buttons in the tracking timeline. I prefer to use shortcuts. As we already know, Ctrl-T will track the selected markers forward. Pressing Shift-Ctrl-T will track the selected markers backward. Alt-right arrow will track the selected markers forward by 1 frame. Alt-left arrow will track the selected markers backward by 1 frame. When tracking, the X and Y position of each marker is keyframed and stored in the timeline. I press Ctrl-Z to undo so that I only have the first marker again. Select your marker and press Ctrl-T to track it forward. If a marker stops close to the edge, you can scale it down and track again to get an extra tracked frame out of it. But once a marker goes off screen, there's nothing more we can adjust. I'll add another marker at a point of contrast. Adjust the position so that the pattern is centered inside the tracker. Then press Ctrl-T again. The track might stop at a frame because it encountered some issues. When that happens, just reposition the marker onto the pattern. Adjust the pattern and search size, then track again. Here it reached the edge of the footage again. In the right track panel under Track, there's a magnified view of your marker's position. You can scrub through the timeline to see if the marker goes off track at any point. At the point where the marker stopped and we started tracking again, there's a spike in the track. You can see this both in the graph editor and in the track path in the viewport. When this happens, go to that frame and realign it. The new position of the marker will automatically be keyframed. There are no other spikes in the graph, so I'll continue by adding a new marker, this time further away. This is important for Blender to calculate parallax. Features closer to the camera move faster than those further back. Parallax just means how much nearby and distant objects shift against each other when the camera moves. The more parallax your footage has, the easier it is for Blender to figure out the camera's movement in 3D. This is good to keep in mind when filming your own motion tracking footage. Moving the camera sideways, forward, or backward while filming will create more parallax and make it easier to get a good solve in Blender. This track went all the way to the end. Features farther away move much slower, so they're often more stable to track. This can also be seen by the relatively flat graph of the track, which indicates that the movement stays pretty much the same throughout. Since this one was so successful, I'll add another one close by. Making the search size smaller allows Blender to track it much faster. Since the movement is minimal when the marker is farther away, the position won't change that much between frames, and the search size doesn't need to be that big. This one also looks very successful. You can tell because there are no spikes in the graph. This pattern looks very clear, so let's track it. This one had some issues at the end. I'll go back in the timeline to before these spikes in the graph start. This feature is much closer to the camera, so there's a larger change in position between frames. The pattern became larger and the inner boundary adjusted its scale to match, but the search size did not, and it became too small for the track to continue. In these cases, you can shift select to scale up only the search size, then track again. Now the tracker reached the edge. You can also track backwards. I'll go to the end of the footage to find a good point on the floor to track. The point is a bit difficult to find at the beginning of the clip, so I'll set a marker at the end where the feature is clear and we can track backwards from there. Adjust the size, then press Ctrl-Shift-T to track backwards. If it slips or stops, just reposition, adjust the size, and track again. Repeat the same process each time it stops. It's okay if trackers scale or skew in the viewport as long as the center follows the point accurately. The X and Y location of the center is the most important and will be used for solving. That's why it's also a good idea to look out for extreme spikes in the graph. The tracker looks a bit spiky in the graph during this segment. In the left track panel, there are a couple of more buttons that might be useful. The clear buttons clear selected tracks before or after any position in the clip. There are also buttons to refine tracks forward or backward from any point. In some situations, these might help smooth out your tracks. But it didn't do much in this case. I'll leave this tracker as it is for now and adjust it later if needed. Let's try another point on the floor. Just press Ctrl-T to track forward, adjust it every time it stops, and track forward again until it goes off frame. This letter A also looks like a good tracking point. Clear shapes like this might help Blender recognize rotation. The search size often gets too small and needs to be scaled up. This next point couldn't even get past a few frames. Sometimes it's better to just delete a marker and try to find a better feature to track. This one got quite far, so I'll go ahead and track it to the end. Intersections such as this one can also be good tracking points. No issues, looking good, so let's move on. When tracking lines like this, put the marker at the end rather than in the middle. Otherwise, the tracker doesn't know where the pattern starts or ends, and it'll start gliding. Let's try this dent. The graph looks good, so I think I'm happy with that. Next, I'll try this corner. That made it all the way to the edge of the clip. Let's try this intersection down here too. I'll track this one backwards. If a track keeps having issues, you can also try adjusting its tracking settings. For example, you could change the motion model. Here I switch to affine because the pattern I'm tracking might get skewed. You could also change the match type, but I'll stick with keyframe. You can always make changes to individual trackers like this throughout the timeline. Affine seemed to do the trick, and the track got quite far, but I started tracking backwards from the wrong frame. I'll go back to that frame and just track it forward for the rest of the clip. We have two trackers on this side of the tunnel, so let's add some on the other side too. The shadow on this corner makes it a bit difficult to track, and it's not getting very far. I think I'll give up on this one. What about down here? Since the opposite side worked well with affine, I'll try to use that here too. With some correction, it worked fine. I'll also add another marker in the foreground. As I mentioned earlier, it's good to add markers at different distances from the camera. This corner has very sharp contrast between light and shadow, so it might work well. When this marker reaches the end, it jumps a little bit. In these situations, it might be a good idea to set a margin. I'll undo a couple of steps. In the right track panel, I'll set a margin of 50 pixels. Now the tracker stops when it's 50 pixels away from the edge. By doing so, we got rid of the jump at the end. I'll add another tracker on the other side. Every newly created marker still has the margin set to 0, but we can copy the settings from the other marker. To do this, Shift-select the other marker and then right-click. Then click Copy Track Settings. Now this tracker also has a margin of 50. Make sure you only have the marker you want to track selected before tracking or making any additional changes. Otherwise, you might accidentally make changes to other tracks as well. In fact, we can select all of our markers with A and press Ctrl L to lock them. Now no accidental changes can be made to them. If you want to unlock selected markers, press Alt L. Then you can continue tracking. Next, I'll add a marker at the top of the footage around the lamp. And another one here. This one jumps a bit at the end. You could of course adjust these keyframes manually, but sometimes if there are drastic changes in light, you can try turning on Normalize. I'll undo a couple of steps and enable Normalize for this marker in the right track panel. This time the track actually followed through better, but this last frame still looks a bit off. Instead of setting a margin and tracking again, I'll just clear it with the Clear Forward button. At this point, I'm just adding some extra markers. You need to have at least 8 tracks to solve the camera motion. However, there will always be some weaker ones. Having extra markers allows you to delete some or decrease the influence of the weaker ones if needed. In the track dropdown, there are also buttons Join Tracks and Average Tracks. Join Tracks combines multiple tracks into one. For example, when a track stops, I can create a new track at the exact same spot, then track it forward and repeat the process every time a tracker stops. At the end, I can shift select all of the trackers and press Join Tracks to combine them. This can be useful if you want to track segments separately. Join Tracks can also be used to combine overlapping tracks. Here I add another tracker to demonstrate. You can also select tracks and press Average Tracks. This creates a new track that averages the motion of the selected tracks. I averaged these 2 tracks to get one clean, stable track in the middle. It smooths out small inconsistencies between them and can give a better representation of the overall motion on this surface. Increasing the search area can help stabilize uneven tracks. If you remember, there was a track from before that was a little bit unstable. Let me go to the point where the graph spikes stop. Then I'll increase the search area and track backwards again. As you can see, that made the track smoother. However, keep in mind that a larger search area takes more computational power, so the tracking process might slow down. The last thing I want to show you before we move on is stabilization. In the right panel, go to the Stabilization tab. Here we can enable 2D stabilization. By default, it only stabilizes the location, but you can also enable rotation and scale options if needed. Then you can add tracks to calculate the stabilization by pressing the plus icon. For location stabilization, you only need 1 tracker. For rotation and scale stabilization, you need at least 2 trackers. The anchor frame sets a reference frame that the trackers will stabilize toward. I'll pick a frame in the middle where the footage looks pretty straight. Then to see the stabilization results in the viewport, go to Clip Display and enable Show Stable. You can see that the camera has been stabilized toward how it looked in the anchor frame, most noticeably the rotation. Autoscale will automatically zoom in and scale the footage to avoid black edges caused by stabilization. You can also set a max scale limit for autoscaling, or disable it and manually adjust the stabilization values. The influence sliders allow you to reduce the intensity of the stabilization effect. The interpolate option controls how pixels are blended after stabilization. You can just choose bilinear for a good balance of quality and performance. Now we can see the stabilization results in the viewport, but to actually apply the effect to your footage, you need to use the Compositor. Add a movie clip node and select the footage that's loaded in the motion tracking workspace. Then add a Stabilize 2D node and select the same footage there as well. Then connect Movie Clip to Stabilize 2D and then to the Composite node. There's also an invert option, which reverses the stabilization effect. This can be used if you want to intentionally reintroduce the original camera motion. Now, if you were to render, the stabilization effect will be applied to the final composite. But we're not going to use stabilization for this project, so I'll delete these nodes and go back. I'll disable 2D stabilization. In the tracking timeline, you have a good track if all of the graphs look similar to each other and have the same shape of spikes. This means that the X and Y location of each marker is moving roughly the same way. However, sometimes you'll get graphs branching off like this. That's just because markers closer to the camera move faster and therefore show a stronger change in the graph, whereas markers farther away move slower and more steadily. And now we're finished with the manual tracking part. Now that we've covered tracking, the next step is camera solving. Go to the Solve tab in the left panel. Again, the solving process is similar to the quick method, but this time I'll mention some new tools and explain things in a bit more detail. First, let's take another look at the cleanup menu. These options are useful for cleaning a large number of tracks at once, like the hundreds of tracks we had during the quick method. However, since we don't have that many tracks using the manual method, we can just fix any problems manually. But I'll quickly go over the options we didn't cover earlier so you know what they do. In the Type drop-down, you can specify what action Blender takes after pressing the Clean Tracks button. Select will simply select the bad tracks. Delete track will automatically delete them. Delete segments will delete only the bad parts of a track. I usually leave it on select so I can analyze the tracks first and decide whether to fix or delete them. The frames value sets the minimum number of frames each track must last for. For example, if I set this to 50, any marker that runs for fewer than 50 frames will get selected. Similarly, the error value sets a maximum allowed solve error for each track. If a track's error is higher than that, it will be selected. I'll explain more about solve error in a moment. Then you can press Clean Tracks to start the process. Filter targets tracks with sudden spikes in their motion curves. Next, let's take a look at the options in the Solve drop-down menu. Tripod is for footage that only rotates without moving, like when shot on a tripod. Then there's Keyframe. Earlier, we enabled this to let Blender automatically select 2 keyframes to estimate the camera motion. You can also define them manually using keyframe A and keyframe B. You want these keyframes to be far enough apart so the camera has clearly moved between them. For most handheld or slow-moving shots, 30 frames apart is a good starting point. If the camera moves very slowly, you can stretch it to 40 to 60 frames apart. If it moves very quickly, 5 to 10 frames between them is usually enough. To choose which keyframes to use, find a spot in the timeline with lots of stable markers. If your scene has strong perspective changes, also called parallax, including those frames can help Blender better understand the 3D camera motion. But this shot moves fairly consistently, so I'll just pick 2 keyframes, about 30 frames apart, in the middle of the clip, where there are many stable trackers. Next, focal length allows Blender to estimate your focal length automatically. If you already know it, you can enter the value in the camera settings on the right. That'll make your track even more accurate. But since we don't, we'll let Blender calculate it, and it usually does a pretty good job. The optical center is where the lens and sensor align. This option also exists in the camera settings, but it's best to enable it here and let Blender calculate it for you. Enabling radial distortion lets Blender calculate lens distortion automatically. In the last video, I showed how to enter distortion values manually, but we'll let Blender handle it this time too. There's also tangential distortion, which corrects skewed or tilted distortion. This is uncommon for regular lenses, so you can usually leave it disabled unless your footage clearly has that issue. By the way, even if you manually specify focal length and distortion values, you can still leave these checkboxes enabled. Blender will use your values as a base and refine them to improve accuracy. Or you can uncheck them if you want Blender to use your exact values without modification. Finally, let's solve the camera motion. Before solving, each marker is just a 2D track. Blender only knows how it moves across the screen, not where it is in 3D space. Click Solve Camera Motion. After solving, Blender figures out the camera's movement in 3D and calculates a 3D position for each track based on how it moves in the footage. The solve error value in the upper right shows how closely these 3D positions match the original 2D tracks. In other words, how accurate the camera motion solution is. It's measured in pixels, so a lower number means the 3D solution aligns more precisely with the footage. If your solve error is above 1 pixel, it's usually unreliable. The camera motion won't line up well with your scene, and 3D objects will appear to slide or drift. If it's below 1 pixel, it's generally usable for simple composites or background replacements, where perfect alignment isn't critical. If it's below 0.5 pixels, that's a solid solve, good enough for most VFX shots where 3D objects need to stay locked to the footage. And if it's under 0.3 pixels, that's ideal. It means your tracking is very accurate and you can confidently add detailed 3D elements or complex animations without visible drift. My solve error right now is 0.41, which falls into the good enough category. But let's try to reduce it a bit. Instead of cleaning or deleting tracks in bulk, like in the quick method, we'll troubleshoot individual markers and fix issues manually this time. To troubleshoot high solve errors, open the Clip Display dropdown and enable Info. In Blender 5.0, this can be found under Viewport Overlays. This lets you see the average error for each track. If any have a very high error, you can delete them and then solve the camera motion again. These tracks have a low error and look good. Some are slightly above 0.5 pixels, but that's okay since most are still below it. This one, however, has a noticeably higher error. There are a few ways to fix this. First, you could try retracking the problematic marker using the previous frame match type instead of keyframe. Since the track is still locked, press Alt-L to unlock it, then press Ctrl-T to track forward. This will override the old keyframes. Check the tracker's error and overall solve error again, then press Solve Camera Motion once more. This actually reduced the solve error significantly. Maybe the pattern changed perspective and previous frame could follow it better. The key takeaway is, if a track is weak, you can always retrack it more accurately or tweak settings and solve again. Here's another marker with a slightly high error, but still within an acceptable range. Let's try retracking it using previous frame and solving again. In this case, the error got worse, so I'll undo those changes. I don't want to delete this track, it's near the center of the frame and could still be useful when setting up the scene. Instead, I'll show you another option in the track panel on the right. The weight value controls how much influence that track has on the overall camera solve. Reducing the weight means it has less influence. I'll lower it to 0.7 and solve again. That worked well. With this weaker track contributing less to the solve, the overall error went down, and as a result, its own average error decreased too. This doesn't make the tracking of that tracker itself more accurate, it just tells Blender to rely on it less during the solve. That way, we can still keep it for setting up the scene later without deleting it. There are a few other markers with slightly high errors, but still within usable range. I'll lower their weights a bit too. Just don't overdo it. If you reduce the weight on too many markers, Blender won't have enough data to solve accurately. But since I have several other solid tracks in the same area, it's safe to lower the weaker ones slightly. Below that, there's also a weight stabilization setting. It reduces the tracker's influence on stabilization, but we're not using stabilization for this shot. You can also change the color of trackers here. That can be useful if you're tracking different areas or objects separately. To do this, select the marker, then choose a preset or set a custom color. So to summarize, to lower the solve error, you can retrack markers for better results, reduce the weight of weaker ones, or delete problematic tracks entirely. You can also keep adding new markers on better features to expand your data. Solve the camera motion after each change and repeat until you reach a good solve error. In this case, my solve error is 0.37 pixels. Not perfect, but good enough to move on. Before we continue, I just wanted to point out that this floor was a bit tricky to track because it lacked distinct features. When choosing your footage or location, it's best to go for one with clear contrast points. It'll make tracking much easier later on. And that's how you motion track using the manual method. As you've probably noticed, this process takes quite a bit longer, which is why I usually prefer the quick method for camera tracking. However, if you run into a situation where Blender can't automatically track the features, or if your system struggles to handle hundreds of markers at once, you now know how to adapt by tracking manually. Now that I've shown you both the quick and manual ways to motion track and solve your footage, let's move on to setting up the scene. I'll continue using the manually tracked data, where I used location, rotation and scale to track the features in the footage with a lot fewer markers, just to show you that this method still works perfectly fine. But if you use the quick method, which actually gave an even better solve, you can absolutely continue with that one instead. Inside the Solve tab on the left, open the Scene Setup drop-down menu. Click on Set as Background. This will make your image sequence visible in the background of your scene camera once it has been added and the scene has been set up in the next step. Next, click on Set Up Tracking Scene. Let's go to the 3D Layout workspace to see what has been added to the viewport and what changes have been made. In the outliner, two collections have been added, foreground and background. The foreground collection contains a cube that we'll replace with our own 3D object. I'll move the cube up so that it sits on the floor. My cube is red because I have face orientation enabled in the overlays menu. Red indicates that the faces are pointing in the wrong direction. To fix this, I'll select all faces in edit mode, then press Shift-N to flip the normals. I'm not sure why Blender created the object like this, but it doesn't matter in our case because we'll delete it later anyways. The background collection contains a plane that will catch the shadow of the 3D object. Select the plane, make sure that you are in cycles, then go into the object data properties. Scroll down a bit and open the visibility drop-down. Here you can see that a shadow catcher mask has automatically been enabled. This makes the object itself invisible in renders, but it still catches and displays the shadows cast on it, but more on that later. Both the foreground and background collections also contain a light. This is actually just one light object that Blender has automatically linked to both collections. It's set up this way because the foreground and background will be rendered as separate layers, which I'll show you in a moment. Blender links the same light to both so that each layer uses identical lighting for consistent and realistic results. However, creating a linked light like this doesn't really serve any special purpose in our case. A single light placed outside of these collections would affect both in exactly the same way. Blender just does it this way to make it visually clear that the light is shared between the two collections. In the View Layer drop-down in the upper right, you can see the foreground and background layers. Scene layers in Blender allow you to separate renders into different layers, then composite them together later in post-processing. As I mentioned, we are going to render the foreground and background collections separately. The foreground layer will only have the 3D object, and the background layer will only have the shadows cast by that object. Then, we'll use the Compositor workspace to blend them together. Blender has also automatically set up a group of nodes inside the Compositor, so let's go to the Compositor workspace and take a look. Since backdrop is enabled, we can see our compositing results in the background. You'll need to move one frame forward in the timeline to make the clip load. You can press V to zoom out and Alt-V to zoom in on the background. First, there is our movie clip, containing the image sequence that is loaded in the motion tracking workspace. Next, there is an undistortion node, but in the latest versions of Blender, it's now called movie distortion. This removes lens distortion from the footage, based on the distortion values that Blender calculated when we enabled the radial distortion checkbox while solving the camera motion. If you enter distortion coefficients manually in the camera settings, those values will be used instead. The scale node is used to scale the footage. Right now it's set to stretch, which stretches the footage to fit our render resolution. Then there's an alpha over node. This node blends two layers together. For example, this group of nodes contains our footage and is plugged into the top socket of the alpha over node. Below the movie clip, we have a render layer node. This node will contain the render of our background layer, which includes the shadows, and it's connected to the bottom socket of the alpha over node. The inputs are then blended together from top to bottom, meaning the movie clip is calculated first, and then the background layer is placed on top. This blend of layers then goes into another alpha over node. Next is another render layer, which will contain the render of our foreground layer. The foreground layer contains the actual 3D object and goes into the bottom socket of the second alpha over node. So the layers are stacked in this order. First the footage, then the shadows, and finally the 3D object, giving the illusion that the 3D object is actually in our environment. This will become more apparent once we actually have something to render. This second alpha over node then connects to both a composite node and a viewer node. The composite node is the final output for our render, while the viewer node lets us see a preview of the composite in the background. I'll go over compositing in more detail in the next tutorial. For now, I just want to show you what's created when you click Setup Tracking Scene. Let's go back to the 3D layout. A camera has also been added. Press 0 on the numpad to go to camera view. The image sequence was already set as the camera background when we clicked Set as Background during the scene setup process. This makes working much easier, as we can see where our 3D objects will appear in the footage while scrubbing through the timeline. However, the objects in our scene don't align with the footage yet, so let's fix that. Go back to the motion tracking workspace. Drag to open a new window and set it to 3D viewport so we can see the changes being made. Hover over the 3D viewport window and press numpad 0 to go to camera view. In the left panel under orientation, we have a few options. Floor will align the ground plane to selected markers. We need to select 3 markers on the floor of the footage to use this button. I try to choose markers with the lowest solve error. With 3 markers selected on the floor, click Floor. We'll fix the rest of the orientation in a moment. For situations where your 3D object should sit on the wall instead, you could select 3 markers on the wall and then click Wall. This would align the plane in the viewport to the wall instead of the floor. However, choosing floor is usually the best option to start with. You can always add geometry later on and align it to the wall if needed, but we won't be doing that in this tutorial. Next, there's Set Origin. This moves the scene's origin to the selected marker. It's convenient if the origin is close to where you plan to place your 3D object. I'll select a marker in the middle and press Set Origin. Next, there's Set X-Axis. This defines the X-axis direction toward a selected marker. The direction is based on the origin, which is why we set it first. I'll select the marker to the right of the origin marker and click Set X-axis. You could also select another point in front or behind the origin to define the Y-axis direction by pressing Set Y-axis. Now our scene is correctly aligned in 3D space. However, everything still looks very zoomed in, right? So next, there's Set Scale. This lets us scale the scene to real-world proportions. To set scale, select two markers. Then there's a distance value measured in meters. You'll need to estimate this based on clues in your scene. I'll guess that the distance between these markers is 1 meter, then click Set Scale. Blender then scales the camera and motion tracking data based on that distance value. However, this isn't always accurate and you may need to make adjustments. When you click Set Scale, an adjustment menu also appears. You can use the distance value to fine-tune the scale until it fits the footage better. For example, the default cube in Blender is 2 meters. I'll scale the camera and motion tracking data so that the cube looks to be about the height of a 2-meter tall person standing in the footage. It doesn't have to be exact, just a reasonable approximation. A distance value of 2 looks okay in my case. Yours might be slightly different, adjust until it looks right. There's also an Apply Scale button. Apply Scale permanently resizes the solved camera and point data to match your chosen scene scale. This might be useful for physics simulations, where applied transformations are important, but we don't need to click it in our case. Now the orientation and scale of our scene are set up correctly. Blender can also display the reconstructed 3D tracks from your solve in the viewport. They can be toggled on and off under Viewport Overlays, Motion Tracking. These are useful for checking how accurately your tracking points were reconstructed in 3D space, and for adding 3D objects more precisely. For example, I used them as a guide when placing the poster before. Next, let's prepare our layers for a test render. Before that, I'll go into edit mode and adjust the size of the plane to fit the floor in our footage. Then I'll replace the cube object with a sphere, just because it looks nicer. Just make sure that the sphere or whatever 3D object you're adding is inside of the foreground collection. Right now, we're still inside the foreground layer. Disable the background collection with the shadow catcher plane so that only the 3D object is rendered in this layer. Then switch to the background layer. Here, we only want to render the shadows cast from the 3D object. However, we don't want to completely disable the foreground collection with the 3D object. We still want it to cast a shadow while being invisible in this layer's render. For that, we'll use the filter drop-down in the outliner. Let me briefly explain what each of these filter icons does. All of these apply to both objects and collections, and they appear next to their names in the outliner once the filter icons are enabled. The checkmark icon completely excludes an item from the current view layer and also disables it from appearing in renders. The cursor icon controls whether an item can be selected. The eye icon controls viewport visibility for the active view layer and is mainly used to temporarily hide items while working. The screen icon controls global viewport visibility, hiding the item in all view layers, though it can still appear in renders. The camera icon determines whether the item is included in renders. The hole icon allows you to use an item as a mask, excluding it from the final render. And finally, the arrow icon makes the item invisible directly, but its indirect effects, such as light bounces and shadows, are still visible. That's exactly what we want to use for our foreground collection. Enabling this allows the objects inside the collection to cast shadows, while the objects themselves remain invisible in the render. You can see this if you go to Rendered View. If you toggle the Indirect Only filter off, the object will appear again, but the object itself will already be rendered in the foreground layer, and we're in the background layer now. We want to adjust the object and the shadows separately. So in this background layer, enable this filter for the foreground collection. The object becomes invisible, but the shadows remain, which is exactly what we want. I'll go back into Solid View and press F12 to render. The layers have been successfully composited. The first layer is the footage. Next, the background render layer with the shadows is added on top. And finally, the foreground layer with the object is placed above the shadows. If your lighting looks a bit different from mine, it's because I have an HDRI set up. An HDRI in Blender is a high dynamic range image. It's used for realistic lighting, reflections, and environment backgrounds. To download an HDRI, go to polyhaven.com, go to Assets, HDRIs, and pick one that matches the lighting in your footage. Every time I open Blender, I have a default HDRI set up. It's called Abandoned Slipway. It's an overcast HDRI that provides neutral fill lighting. Select 4K, EXR, and click Download. Save this inside your project folder. I created a new folder called HDRI for this file. Inside Blender, open a new window and set it to Shader Editor. Set the shader type to World. I already have an HDRI set up, but your workspace probably only has the default background node. In Edit, Preferences, Add-ons, make sure Node Wrangler is enabled, then click Save Preferences. In the Shader Editor, select the background node and press Ctrl-T. This will set up the nodes needed for the HDRI environment. Click Open and select the HDRI file you just downloaded. Now the HDRI has been added as the world background. Go to Render Preview. If your background isn't transparent like mine, go to Render Properties, Film, and enable Transparent. Now the HDRI provides lighting to the scene while being invisible in the background. Your lighting should now look similar to mine. Lastly, I'll scale the sphere down a bit and center it inside this archway. This time, I want to render a test animation. Go to Output Properties. Set the resolution and frame rate. I'll render this test animation in 1080p using the same frame rate as the original footage. Set an output folder for your animation and give it an appropriate name. Change the file format to FFmpeg video. Under encoding, select MPEG-4 as the container. Go back to Solid View, then press Ctrl F12 to render the animation. And here's what the animation looks like so far. I hope that you were able to follow along and achieve a similar result. Okay, that's all for this video. Well done making it this far. If you found this video helpful, I'd really appreciate it if you dropped a like. There was a lot to take in this time, but you can always go back and review specific sections if you forget something. Be sure to subscribe if you want to follow along with the next tutorial, where I'll show you how to download and add 3D models, create realistic lighting, and use the Compositor to blend the 3D objects into your footage. Finally, I'll show you how to download sound effects and use another free software to edit them. See you all in the next episode.